I will start today's lecture by reminding you of the kind of tedious process by which one computes a determinant. We will then turn to the question of whether or not it might be possible to use elementary row operations to make it easier to compute the determinant. And we will finish by proving that the determinant of a matrix is zero if and only if, the determinant is non-zero if and only if the matrix is invertible. So are there questions from the last lecture? I haven't convinced you of what the determinant is useful for, other than it's being a diagnostic for invertibility. We will find the determinant to be quite useful later on. So at the moment, it just seems like some weird number that we're asking you to compute from a square matrix. Because you already know if I give you a square matrix, the fastest way to find if it's invertible is you just make that augmented matrix A identity. You do the elementary row operations, which you're comfortable with from chapter 2. And you basically figure out is A row equivalent to the identity matrix. So given a specific matrix, you already know how to quickly check if it's invertible. All right, so let's just consider the following matrix. A is 2, 2, 4, 3, 6, 6, 1, 2, 1. Now, from last time, we know that computing the determinant basically means picking a row or picking a column, and then doing some sort of procedure along that row or some procedure along that column. And from last time, we saw that freedom of choice made it super easy to compute the determinant of an upper triangular matrix, a lower triangular matrix, a diagonal matrix. Having the freedom of choice on column or row made us be able to see and understand some things very easily. And usually our method was to find a row or column that has a whole bunch of zeros in it. Now, with this matrix, there is no row or column that has a whole bunch of zeros in it. And so ultimately, it doesn't really matter which row or column we use to compute the determinant, because no matter what, it's a full matrix. So there's no low-hanging fruit to choose, because for every zero in that row or column you choose, that's one less determinant you have to compute, cofactor you have to compute. So it doesn't matter which row or column we choose. So let's just choose one at random. I'll choose this one because it's a little bit different. So what I do is the determinant of A is going to be A 1, 2 times the 1, 2 cofactor plus A 2, 2 times the 2, 2 cofactor plus A 3, 2 times the 3, 2 cofactor. That's just the definition of how to compute a determinant. So A12 is 2. The 1, 2 cofactor is minus 1 to the 1 plus 2 times the determinant of the smaller matrix that I get by removing the first row and the second column. So that's 3, 6, 1, 1. That was just this. Now we have A22. A22 is 6. Now I have the 2, 2 cofactor. So that's minus 1 to the 2 plus 2 times the determinant of. I take out the second row and the second column because it's the second row, second column cofactor. That gives me 2, 4, 1, 1. And then that was this term. Now I do A32. Well, A32 is 2, and then I do the 3, 2 cofactor. So that's minus 1 to the 3 plus 2 times the determinant of the matrix that I get when I remove the third row and the second column. That is 2, 4, 3, 6. And I chunk through that, and I finally get the answer of minus 6. So that's kind of, it's doable. You could do it on a test. It's just 3 by 3. But now imagine if A were 4 by 4 and didn't have any zeros to help you. or if A were 5 by 5 and didn't have any zeros to help you. If you were given a 4 by 4 matrix with no zeros to help you, you'd have to compute, so you're given a 4 by 4 matrix. To compute its determinant, what kind of, you're going to have to compute a bunch of 3 by 3 determinants. How many of them? 4. Now for each of those 3 by 3 determinants, you're going to have to compute a bunch of 2 by 2 determinants. How many? 3. So you're going to have to compute 12 2 by 2 determinants, a whole bunch of -1s to the something or another, and you don't have any zeros to help you out. You can do it on a test, but I don't recommend it. So the question is, what's the alternate approach? So if we take A, so we have 2, 2, 4, 3, 6, 6, 1, 2, 1. Let's do some elementary row operations. So let's swap rows 1 and rows 3. So 1, 2, 1, 3, 6, 6, 2, 2, 4. This is then row equivalent to 1, 2, 1. Let's use this to knock that out. So this minus 3 of that is 0. This minus 3 of that is 0. This minus 3 of that is 3. 2, 2, 4. So that's going to be row equivalent to 1, 2, 1, 0, 0, 3. This minus 2 of that is 0. This minus 2 of that is minus 2. This minus 2 of that is 2. Whoops. Now, if I want, I could swap the rows. 1, 2, 1, 0, 0, whoops, swap the rows. 0, minus 2, 2, 0, 0, 3. What is the determinant of this? Minus 6. What is the determinant of this? Negative 6, after having done a bunch of work. So we would like to know whether this is a coincidence or not. So before we leap to any conclusions, let's compute the determinant of this one. So you're going to expand about 2 good choices. What are 2 good choices? First column or second row. So if we expand about the first column, we're going to get 1 times the determinant of this puppy, which is what? Negative 6. Whoa, hold on. 1 times the determinant of this? 6. Now, so the determinant of this was 6, and the determinant of that was minus 6. So we see for sure that elementary row operations, it's not just like the determinants remain unchanged, because right here we did an elementary row operation, and the determinant went from 6 to minus 6. But maybe if we had some way of keeping track of what happened to the determinant every time we did an elementary row operation, we might be able to reverse engineer things. So that's the idea. The idea is if we knew what the determinant did to each elementary row operation, what each elementary row operation did to the determinant, then we could reverse engineer. So here are the facts that you're going to, I'm just going to state them for the moment. So fact 1, if you create B by multiplying a row of A by T, then the determinant of B equals T times the determinant of A. That's a fact, and we'll be able to prove it. Okay, how can you remember? How can you remember it? Well, let's take A is 2, 0, 0, 3. Let's take B is 2, 0, 0, 0, 3T. I got B by multiplying this row by T, right? The determinant of B is what? 6T. But I'm going to write it as 2 times 3T. That's equal to T times 2 times 3, which is T times determinant of A. This isn't a proof of this statement. This is simply how you can remember it. Okay, fact 2. If you create B by swapping 2 rows of A, then the determinant of B is equal to minus the determinant of A. To remember, this isn't a proof, it's how you can remember that this should be true. If A is 2, 0, 0, 3, and B is 0, 3, 2, 0, then the determinant of B is equal to -6, which is the negative of the determinant of A. So if you are ever having a moment of crisis where you're like, I forgot the rule, try the rule on a simple diagonal matrix. It's not a proof, but it's a way to remember. Fact 3. If you create B by adding a multiple of one row of A to another row of A, then the determinant of B equals the determinant of A. To remember, so A is 2, 0, 0, 3. B is 2, 0, 2T, 3. So I took T times the first row and added it to the second. Determinant of B is what? 6 is the determinant of A. This is not a proof. This is a way for you to remember this fact. So are there questions? We will get to how to prove these facts by the end of class. But right now, we just want to use them. So let's go back to our example, that one. So let's do it slowly. So we had A, which was 2, 2, 4, 3, 6, 6, 1, 2, 1. It's not my phone. Yes. And this is row equivalent to the matrix 1, 2, 1, 3, 6, 6, 2, 2, 4. I swapped rows 1 and rows 3. This is B1. By my facts, the determinant of B1 is related how to the determinant of A? Minus the determinant of A. So we just used fact 2. Now, B1, which is 1, 2, 1, 3, 6, 6, 2, 2, 4, if I send row 2 to row 2 minus 3, row 1, I get the matrix, I guess that was a tilde. I get the matrix 1, 2, 1, 2, 2, 4, and I had 0, 0, 3. So this is B2. The determinant of B2 is related how to the determinant of B1? They're the same. Which fact? Fact 3. Now, B2 is 1, 2, 1, 0, 0, 3, 2, 2, 4. That's row equivalent to, if I sent row 3 to row 3 minus 2, row 1. And that gave me the matrix 1, 2, 1, 0, 0, 3, 0, minus 2, 2. So that's B3. And the determinant of B3 is equal to, how is it related to the determinant of B2? It's the same. And which fact was that? Fact 3. Now, I'm going to take this all the way. So at this point, actually, let's pause for a moment, because at this point, this is a matrix whose determinant you can easily compute. So if you had been taking a test, and you were just asked, what is the determinant of this huge matrix? Imagine it's 4 by 4. And you got it all the way to something like this, which you could compute easily. All you were asked was the determinant. At this point, you can stop. Is this in reduced row echelon form? No. Do you care in terms of computing the determinant? No. So let's pause. So you've gotten this far in the game, and you're like happy because the determinant of B3 is something you can compute. The determinant of B3 was 6. So this is going to tell us that the determinant of B2 is equal to what? 6. Because determinant B3 equals determinant B2. This is going to tell us that the determinant of B1 is equal to 6. Because the determinant of B2 equals the determinant of B1. This is going to tell us that the determinant of A is equal to negative 6. Because the determinant of B1 is the negative of the determinant of A. And so then you put a little box around this and you turn the page. But let's keep going. So let's take this all the way to reduced row echelon form. So we have B3, which is 1, 2, 1, 0, 0, 3, 0, minus 2, 2. I'm going to swap rows 2 and rows 3. Row 3 and row 2 are swapped. And I get 1, 2, 1, 0, minus 2, 2, 0, 0, 3. This is B4. So I know that the determinant of B4 is related how to the determinant of B3? Negative. Now I'm going to, so I've got B4, which is 1, 2, 1, 0, minus 2, 2, 0, 0, 3. And that's row equivalent. I'm going to send row 2 to minus 1/2 times row 2. So 1, 2, 1, 0, 1, minus 1, 0, 0, 3. That's B5. The determinant of B5 okay, we're going to have to use which fact? Fact 1. What is T? Negative 1/2. Determinant B4. Let's keep going. So B5 is 1, 2, 1, 0, 1, minus 1, 0, 0, 3. This is row equivalent to I'm going to send row 3 to 1/3 row 3. And that gives me the matrix 1, 2, 1, 0, 1, minus 1, 0, 0, 1. This is B6. And the determinant of B6 is equal to what? 1/3 determinant of B5. Now I'm going to take B6, which is 1, 2, 1, 0, 1, minus 1, 0, 0, 1. And I'm going to subtract 2 of this row from that row. I'm going to subtract this row from that row. I'm going to add this row to that row. And I'm going to get what matrix? Let's do that one more time. This row minus 2 of that row. What did I just kill? I killed that. And then this became a 3. I should have done it more slowly. This became a 3. Now, I've got this 1. So I'm going to do, after I've killed that 2, I shouldn't be so brutal. After I have sent that 2 to 0, I will now, I've got a new row 1. I will now subtract 3 of this from that. This 3 will be sent to 0. I will add this to that. This minus 1 will be sent to 0. And I will have this. Now, how is the determinant of B7 related to the determinant of B6? It's the same. I used fact 3 how many times? 3 times. OK, so now, here we go. The determinant of B7 is what? 1. Now, this tells us, because it was easy to compute. You always start at some point that's easy to compute. This tells us that the determinant of B6 is what? 1. We use this. This tells us that the determinant of B5, so you have to use this, is 3. This tells us that the determinant of B4, where did determinant B4? Here. -6. And now I can go all the way down to the determinant of A if I wanted. So I wanted to do this for 2 reasons. The first reason is I didn't use fact 1 before. And I wanted to show you how fact 1 affects things. The second reason I did this is to convince you that if all I needed was the determinant of A, I could have stopped at B, whatever it was, B3. The third reason, -1/2, is this equal to 0? No. 1/3, is this equal to 0? If I get that this has determinant 1, can any of the previous determinants equal 0? No. This means that if A is row equivalent to the identity matrix, can its determinant be 0? So you've got some A, and you do a whole bunch of stuff, and you carry it to the identity matrix. The determinant of the identity matrix is 1. When you start going backwards and reverse engineering to get the determinant of the original matrix, sometimes nothing happens, because you had used fact 3. Sometimes you multiply by -1, because you had used fact 2. Sometimes you multiply by a number. Is that number ever 0?
No.
No. So you do a whole bunch of stuff, and you end up at the determinant of A. If you started out with determinant equals 1, can the determinant of A ever be 0? No. That's actually the proof of our theorem, that if the determinant is non-zero, sorry, if A is invertible, then the determinant is non-zero, and basically that if the determinant is non-zero, then A is invertible. So we'll revisit that at the end of class. If you went through all of this and you ended up with a matrix which had a row of zeros, so you ended up and the determinant of B7 was 0, as you reverse engineer back to A, well, maybe you had 0 and you multiplied it by -1. Or maybe you had 0 and it was 0 in the previous step because you'd used fact 3. Or maybe you had 0 and you multiplied it by a non-zero number. What happens when you take 0 and you multiply it by a non-zero number? 0. So facts 1, facts 2, facts 3, which you apply as you kind of reverse engineer from the determinant of the reduced row echelon form, you're just going to keep getting 0 all the way to the beginning. A is 0. So this basically shows you if the reduced row echelon form of A has a row of zeros, the determinant of A must be 0. If the reduced row echelon form of A is the identity matrix, the determinant of A must be non-zero. And then we just use what we know already about A is invertible if and only if it's equivalent to the identity matrix. So have I convinced you that fact 1, fact 2, fact 3 are useful in terms of simply computing the determinant of that matrix? Yes. Have I convinced you in some sense to believe that these 3 facts are useful in terms of proving that determinant gives you invertibility information and vice versa? Okay, so are there any questions? Yes?
I was wondering, it seems like in most of those steps you use like one of those facts at a time.
Exactly.
Could you maybe put more than one fact at a time?
Well, okay, so the question was, do I do more than one fact at a time? I try not to, because when I'm reverse engineering, I really needed those equations one at a time. The only time I got lazy was when I was at this point, and I realized if I did them one at a time to get 3 equations, really I should have gone B6 to B7, B7 to B8, B8 to B9.
You're already mixing like fact 3 there.
I used and then I'm like, okay, I'm going to run out of Blackboard. Yes, I should really get to B9. But then the determinant of B9 is going to equal the determinant of B8, is going to equal the determinant of B7. So this is the one where I did 3 fact 1s, 3 fact 3s at once. And I did that with confidence because I knew it was just going to be stuttering. But if I'm flipping sign or if I'm using fact 1 or fact 2, I do not do multiple things at once. Fact 3, I do multiple things at once. In general, personally, if all I want is the determinant, I actively avoid fact 1. I do all sorts of swapping, adding, and all of that stuff to get myself to something like this, and then I just compute the determinant. So you can get rid of zeros and stuff. You can introduce zeros and stuff just using facts 2 and facts 3. And if all you want is the determinant, then that means all you want is to introduce a whole bunch of zeros till you have something you can easily compute. And that's good. Having all 3 facts is useful for the theory. Are there other questions? Yes?
Can you just repeat where you get 3 and -6 again?
OK, so the question was this and this. So from this one, I'm going to use the fact I have that determinant B6 is equal to 1/3 of determinant B5. That was this one right here. That tells me that 3 times determinant B6 is equal to determinant B5. I know that determinant B6 is equal to 1, so I have 3 times 1 is determinant B5. Are there other questions? OK. So let's actually try and prove some of these facts. So the proof of fact 1 and the proof of fact 3 are incredibly easy. The proof of fact 2 involves proof by induction, which is one of these great breakthroughs in Western civilization, so I'm going to inflict it on you. Because part of being at university involves becoming cultured. You may never use proof by induction as an engineer, although some engineers actually do use it. Okay, so the proof of so here's the proof of fact 1. So before I get to the proof, I want to explain to you how the proof should work. So I'll do a 3 by 3 case. So A is A11, A12, A13, A21, A22, A23, A31, A32, A33. And B is A11, A12, A13, T times A11, T times A12, T times A13, 21, 22, 23. I'm taking the second row, multiplying it by T. A31, A32, A33. I'm trying to relate the determinant of B to the determinant of A. I can expand. To compute the determinant, I can go about any column, any row. What do you think might be a smart choice of rows?
Make it the same as
So first row, second row, or third row? Second row. So determinant of B is equal to T 21 cofactor 21 plus T A22 cofactor 22 plus T A23 cofactor 23. All right. So that's equal to T times A21 cofactor 21 plus A22 cofactor 22 plus A23 cofactor 23. So let's look at these cofactors. To find the 2,1 cofactor, I'd knock out the second row and the first column. That gives me a 2 by 2 matrix, and I compute its determinant. So this is going to be T times A21 times minus 1 to the 2 plus 1, the determinant of A12, A13, A32, A33, plus all right. So I just wrote down the 2,1 cofactor. If I tried to compute the determinant of A about the second row, I would get A21, C21, and I'll put a tilde just in case, because I don't want, it might be that the cofactor for the A matrix is different. A22, the 2,2 cofactor for A. A32, the 3,2 cofactor for the matrix A. So I want you to look, this is the 2-1 cofactor for A. And this one up there I have the 2-1 cofactor for B. What can you tell me about the 2-1 cofactor for A versus the 2-1 cofactor for B? They're the same. So this tells us that the determinant of A equals A21, the 2-1 cofactor for B, plus A22, the 2-2 cofactor for B, A23, the 2-3 cofactor for B. And so that tells us that the determinant of B is equal to T times the determinant of A. Because the determinant of B was T times that thing. And T times that thing equals the determinant of A because the 2-1 cofactor of A equals the 2-1 cofactor for B, and so on. Because we chose a smart row to expand about. If we had expanded about any other row or column, it would still turn out that the determinant of B equals T times the determinant of A. But it wouldn't be so easy to prove. Okay, so having seen this for a 3x3 matrix, do you believe you could prove it for a 4x4? 5x5? You would just take whatever row it was that got multiplied by T. You would do your cofactor expansion about that row. The key observation is this one, that the 2-1 cofactor for A equals the 2-1 cofactor for B. Once you've removed the offending row, the row that was multiplied by T, all of the cofactors are the same. Okay, so I'm not going to actually, I shouldn't call this a proof. This is the, I'll put it in quotes. If I were to write this out as a full proof, it would just look confusing, unless you're good at reading proofs. This can be written as a proper proof, and some of you should try it. All right. Now we have fact 2, which is swapping two rows means that the determinant of B equals minus the determinant of A. And this is one which I am going to prove, and it's going to be proven by induction. So what proof by induction means for this case is I'm going to manually prove that this is true for 2x2 matrices. Now, I'll then go to the case of 3x3 matrices. I'm going to handle the case of 3x3 matrices using the fact that a 3x3 matrix is written in terms of a bunch of determinants of 2x2 matrices. And I've already proven that it's true for 2x2 matrices. Therefore, I'm going to leverage that information to prove that it's true for 3x3 matrices. So at that point in the game, I'll have proven it for 2x2 matrices and for 3x3 matrices. Now, to prove it for 4x4 matrices, I'll leverage the fact that the determinant of a 4x4 matrix is just a combination of 3x3 determinants. I already know it's true for determinants of 3x3 matrices. Therefore, I will prove it. That will imply it's true for 4x4. Then I'll go to 5x5 matrices. Now, a 5x5 matrix, its determinant is in terms of a bunch of determinants of 4x4 matrices. I've already proven it's true for 4x4 matrices. Therefore, it's true for 5x5. And so on and so on. If I had infinite time, I would prove that it's true for 100 by 100, using that it's true for 99 by 99, and so forth. It's called proof by induction. It's like a stepping stone argument. It's how you prove something is true for every integer, every positive number, every positive integer. OK, so step 1. 2 by 2 matrices. So I have A is A11, A12, A21, A22. If I'm swapping two rows, there's only one option. I have A21, A22, A11, A12. The determinant of B is equal to A21, A12 minus A11, A22, because we know how to compute determinants of 2 by 2 matrices. This is equal to the negative of A11, A22 minus A12, A21, which is equal to the negative of determinant of A. Do you believe that it is true for all 2 by 2 matrices? Because whatever numbers you put in for A11, A12, A21, A22, this is going to be true. Okay. Step 2, 3 by 3 matrices. So A is A11, A12, A13, A21, A22, A23, A31, A32, A33. How many possible swaps are there? Three. So one option is B1, I'll swap rows 1 and rows 2, A11, A12, A13, whoops, hello, 2, 1, 2, 2, 2, 3, 1, 1, A12, A13, A31, A32, A33. Now there are two more swaps. So B2, I'll swap row 1 and row 3, A31, A32, A33, A21, A22, A23, A11, A12, A13. That's swapping rows 1 and rows 3. Final swap is rows 2 and rows 3. So that leaves the first row unchanged. All right, those are the three possible swaps. So now, I want to use the fact that I know it's true for 2 by 2. Which means that when if I'm going to do a cofactor expansion about this one, I want that the lower determinants I have to compute involve swaps. This means I should do a cofactor expansion around a row which does or does not involve swaps. Does or does not? So does not, because if I do a cofactor expansion about this row, I'm going to use these, I'm going to need the determinant of this, which has swaps, or the determinant of this, and so forth. So determinant of B1, I'm going to do around the third row. So that's A31 times the determinant of A22, A23, A12, A13, minus A32 times the determinant of A21, A23, A11, A13, plus the determinant, plus A33 times the determinant of A21, A22, A11, A12. And I want to relate it to the determinant of A, which is, again, going around the third row. It's A31 times the determinant of A12, A13, A22, A23, minus A32, the determinant of A11, A21, A13, A23, plus A33 times the determinant of A11, A12, A21, A22. Okay, so we're looking at these. Determinant of B1 has an A31. Here I have an A31. I have a determinant of a matrix. I have a determinant of a matrix. How is this matrix related to that matrix? Swapping rows. What do I know about determinants of 2 by 2 matrices that have had their rows swapped? They're negatives. Minus A32, minus A32. Here I have a 2 by 2 matrix. Here I have a 2 by 2 matrix. How are they related? They swap 2 rows. But I've already proven by hand that if you swap 2 rows in a 2 by 2 matrix, how are these determinants related? They're the negatives. A33, A33. Determinant of 2 matrices. How are these 2 matrices related? Swap 2 rows. But I've already proven for 2 by 2 matrices that if you swap 2 rows, what do you get? The negative of the determinant. So this is equal to minus the determinant of B because I proved it. I proved what swapping does for 2 by 2 matrices. So that was B1. Now for B2, which row am I going to expand about? So let's look at B2. B2 I got by swapping rows 1s and rows 3. Which row am I going to expand B2 about? Second row. And I'm going to repeat that argument. For B3, I got B3 by swapping rows 2 and 3. So I'm going to expand around the first row. So you saw the proof that the determinant of B1 is the negative of the determinant of A. You now do the proof for B2 and B3. So now I know that swapping 2 rows, I know what it does for 2 by 2 matrices and 3 by 3 matrices. I now can do it for 4 by 4 matrices, and 5 by 5 and 6 by 6. And that's how the proof goes. It's done in the book, and you should look at it. So one important outcome, fact. If A has a repeated row, then the determinant of A equals 0. So certainly you know this for the matrix A, B, A, B. You can compute the determinant. You get AB minus AB. What if I have the matrix A is A, B, C, D, E, F, A, B, C? This is row equivalent by swapping rows 1 and rows 3 to the matrix. OK, ready? Here we go. I'm going to swap them. A, B, C, D, E, F, A, B, C. That is B. By my fact, I know that the determinant of B is equal to what? Well, by my fact involving swapping, it's equal to negative determinant A. Because A had a repeated row, B actually equals A. Therefore, the determinant of B equals the determinant of A. So right here I used that I have a repeated row. So this tells me that the determinant of A equals the negative of the determinant of A, which tells me that the determinant of A equals 0. Do you believe you could do this for a 4x4 case? N by N? Okay, so we did not finish this section. On Monday, we will finish up this section. We want to prove the third fact. The proof of the third fact can be easily done using this. The proof in the book is confusing for no good reason. Please don't pay attention to the proof in the book.